Djordje, if you could share your slides. Okay, that looks good. Please go ahead.
Okay, can you hear me?
Yes.
Okay, perfect. And you can see me and everything works? Okay, excellent.
Yeah, it looks good, yeah.
Okay, thank you. Okay, so thanks everyone for putting together this nice conference and for having me here. Given the time constraints, I decided to give a very short, compact story that may be of interest to many people here, that may be something that a lot of you have kind of internalized, but since it has not been stated very explicitly in the literature to my knowledge, I thought it might be interesting to share it. And those of you who know me will not be surprised that this is a bit weird compared to, you know, the rest of this conference, but I still think it'll be interesting. Okay, so let me immediately continue. Let me just see. Okay, this works, right? You see the next slide. Good. Right, so very appropriately, I will continue where I left off the last time I talked at Simon Center in the days before when it was possible to do that easily in person. So in 2018, at a conference relatively similar to this one, I remarked on a very simple anomaly that you find in lattice theories, a global anomaly. And it was also something that I had not really seen in the literature before. And let me first describe what I told you then, and then I will talk about some new uses for this kind of idea and a new direction to take it in. So take, for example, a theory of spinless fermions on some finite lattice. It doesn't matter what dimension or really what shape. Let's just assume it's orientable, but otherwise arbitrary. And let's just assume the only dynamical thing that I will assume is that there exists a fermion number symmetry that is generated by this operator here called NF. And let's ask what happens when you try to gauge this operator or this symmetry. So to do this in the most elegant and proper way, you should first start by defining a unitary generator for this symmetry, which I've defined here. And you can then realize it, of course, as a product of local operators, locally defined operators, where Q is a representation of the symmetry, or you can just think of it as an integer, and epsilon is some number which for a U1 symmetry will be infinitesimal. And so to gauge the symmetry, follow this very familiar procedure of just introducing gauge fields on links of this lattice and impose the gauge constraint that I have written here. So basically say that locally at every point x, this unitary matter part of the symmetry times this Gauss operator here has to be the identity operator up to some phase. The Gauss operator is, of course, something that just shifts the gauge fields on all the links emanating from a given site by this amount epsilon. So that's all very nice and proper. And that sounds pretty normal. Now, the interesting thing that I want to stress, which I stressed a few years ago as well, is that depending on your choices of Q, epsilon, and these background charges, rho x, this procedure may actually be inconsistent. You may actually not be able to get a nice theory by imposing all of these constraints. For example, a very simple example, if you choose let's say the charge is 1 and choose epsilon to be infinitesimal, so you really have what you would call a U1 symmetry, and choose one of the background charges to be negative, to be just -1, let's say, and all the other ones are 0. If you do this, and remember you're on a finite lattice, then there exists no state that is of matter that's going to satisfy all the gauge constraints. So you can gauge, but you will get an empty Hilbert space. So this is in that way very reminiscent of the really much fancier global anomalies of the kind that Witten discovered in the SU2 QCD kind of theory. And then there's another case, which is sort of a limiting case, where if you take, again, epsilon to be very small, much smaller than all the other scales in the system, and you take all the background fields to be 0, then the only state that's going to satisfy your gauge constraint is going to be the one with no fermions whatsoever. So it's going to be, just an insulating state. So it's sort of quasi-anomalous. There's almost nothing happening in this theory. And the reason why I call this anomaly geometric, back in this paper that I published back in 2018, is because at finite epsilon, something interesting happens, and whether you actually get a non-trivial theory or not after gauging actually subtly depends on number theoretic relations between epsilon, q, rho, and the size of the lattice. So it's actually something that's detected by the geometry of the lattice. So for some choices of epsilon, you may get a theory only if n is even, on the number of sites on the lattice is even or not. So that was a short remark I made that one has to be careful about gauging these symmetries when you're in a completely regularized setting. And now I want to generalize this story a little bit and talk about some other ramifications of essentially the same phenomenon.
Excuse me, is this a Z2 anomaly?
Can we have questions later?
Just ask what is a Z2 class anomaly anyway.
Ask me later, please. I don't want to get too distracted. Anyway, so the origin of this anomaly, ultimately, the reason why this kind of anomaly happens is because the gauge fields, the gauge group is much larger than the target space of the matter theory. So that's one way to think about the origin of this. In particular, if my matter density, this operator J, if that was allowed to have eigenstates that go all the way up to eigenvalues that go all the way up to 1 over epsilon, then I wouldn't have this anomaly. Then I would be able to sort of put enough matter in so that I counterbalance a negative insertion of charge. And a fancier way to say this is that this anomaly occurs because the local symmetry generator does not act faithfully on the matter Hilbert space, on the local Hilbert space of the matter. So I was thinking of calling this a faithless anomaly, but I felt that might get me into trouble. So, but here is the direct consequence of this, a local consequence of this faithlessness. So if we consider this generator raised to some integer power m, then there exists a relation like this. So basically what this says is that these operators for different m are not linearly independent. In fact, for fermions, this is just these are all 2 by 2 matrices. So they're all linearly dependent of each other after the second power. So there is this relation for some simple enough coefficients alpha and beta, which I did not write. And when you use this relation after you've raised the gauge constraint itself to the nth power, you get a relation that looks like this. So you actually get the relation between the Gauss operators in the pure gauge theory, and you no longer have anything to say about matter here. This is an interesting situation. It basically says that if you couple a U1 gauge theory to a matter theory with a finite target space, then you're imposing constraints purely on the matter fields, purely on the gauge fields. And in this particular case, you actually impose so many constraints that you effectively end up decoupling the matter from the gauge field if you end up solving these constraints. So it's actually pretty drastic. If you open a standard lattice gauge theory textbook or something like that, and you look at what people do with QED, you will actually see that this kind of stuff is not often discussed, but this kind of gauging is actually extremely drastic, and it's the same mechanism which, taken globally, may end up leaving you with an empty Hilbert space. It's the same mechanism. It's like they're not exactly the same phenomena. So I now want to stress one consequence of this story. When you actually have actual lattice QED. So that's a theory in which I have more than one spinless fermion, so at least two. Let me call them phi plus and minus, like two components of a two-component spinner. Again, it doesn't matter what dimension I'm in or anything. Like I'm just talking about kinematics. And let's say I want to gauge the total fermion number symmetry, which is now given by a sum of by an exponential of the sum of the fermion densities for each component. And here, turning the crank will generate a different kind of constraint that only becomes simple when you take the matter charge to be very small compared to 1 over epsilon. And for convenience, it's nice to take the system to be at half filling. So you take the background charge to be precisely half of the total possible charge you can put on at each point. So once you do that, you end up with this nice constraint here. And this time you don't necessarily decouple gauge fields from fermions. You actually have some leeway, but to first order in epsilon, it's quite interesting. You actually force all the Gauss operators to satisfy an equation like this, meaning that they must be expressible as exponentials of epsilon times some operator with order 1 eigenvalues. So what I want to say by this is that this constraint ends up forcing your gauge fields to your electric field eigenvalues to be small in some sense. And as far as I'm aware, this is the only rigorous argument that sort of says that if once you have fermions plus U1 gauge fields on a lattice, there's some reason for the fluctuations of the gauge fields to be small. That is actually something that people often take for granted. You write your QED on a lattice or QCD, and then you expand e to the IA into powers of A, or you expand e to the I delta E, like this kind of thing, into powers of delta E. And that's really only, and that's justified post hoc. That's justified by consistency, by looking at consistency conditions of the resulting theory. But it would be nice to know a priori, like whether that is a possibility, whether that has to happen or what are the alternatives. And this is sort of the only way I know how to get at that kind of relation, starting from first principles. And in general, the fact that coupling large gauge groups to small target spaces gives you these interesting constraints is something that I was not familiar with from reading classic papers, but it seems to be something that's very relevant for calculating, for understanding continuum limits of lattice theories, because for continuum limits, you really intrinsically need small fluctuations of your fields. So by the way, this is a very long story that I've been working on for a while. So this week I'm publishing papers on this. So they don't have archive numbers yet, or not all of them have archive numbers yet, but you will see them if you log in a few hours. You will see how I use this kind of stuff in a bigger story about continuum limits of gauge theories. So with this, I will stop. I think that sort of wraps up my short story. And thank you everyone for your attention. And I remain here open for questions.
Great, thanks a lot. Yeah, so now that the